Okay, Bismillahirrahmanirrahim. So last lesson we looked at the mechanism of halogenation. Need password. What is the password? Can someone send this password to Ben? 5SJM0Z. 5SJM0Z. Send it to the group. Okay, so last lesson, we looked at the halogenation of benzene. Okay, so halogenation can be adding chlorine or adding bromine. The same mechanism for the as the general mechanism that I showed you. Okay, so one thing that I probably did not mention, which is minor but still important, in this first step, you have 6 pi electrons inside this ring. Okay, so when an electrophile approaches the benzene, 2 of the pi rings, 2 of the electrons in the pi system, which is a pair, okay, a pair of electrons in the pi system equivalent to 2 electrons, will be given to the electrophile. Okay, so then it forms a carbon-chlorine bond, carbon electrophile bond. In the intermediate, there are only 4 electrons in this broken pi system or broken delocalized system. Okay, so take note, in this complete circle there are 6 pi electrons. In this broken circle there are only 4 pi electrons. Okay, that positive charge is spread out between carbon number 2 to carbon number 6. The carbon hydrogen bond breaks to neutralize this positive charge. Okay, you form a chlorobenzene and a H+. And then we talked about the effect of methyl side chain on the benzene ring. Okay, so you have a methyl group here, which is attached onto the benzene ring. Once the methyl group is attached, it has this electron donating effect. Or another way to look at it is it activates the 2, 4, and 6 position. That means any incoming electrophiles, whether it's chlorine, whether it's bromine, later on you will meet a few more electrophiles, okay? They will sit on position 2 or 4 or 6 or all together, or 2 of them, 2 out of 3 or 3 out of 3. So basically the basic idea is 2, 4, and 6 is activated, the position. Okay, and then we also looked at how the different condition will trigger different type of reactions. Okay, if you use UV light, that is the condition for the reaction of alkane. Therefore, reaction will happen on the alkane part of the molecule. If you use a halogen carrier, that is the condition for the reaction of benzene. That means the reaction will happen on the ring, directly attached to the ring. So you have to be careful with the condition of the reactions and also to identify the type of functional groups that you have in your starting molecule. Okay, like if this is your starting molecule, which is the methyl benzene, the benzene ring is an arene or a benzene functional group. The CH3 on the side chain is an alkane functional group. Okay. This one already. Okay, so this is our next learning objective that we want to cover. We are still going to look at the mechanism of electrophilic substitution, but this time we're going to look at the formation of nitrobenzene. So nitrobenzene is the nitro group, the addition of the nitro group, which is NO2. Okay, here's some information on nitrobenzene that you can read yourself later on. right? So if you want to add the nitro group onto your benzene ring, these are the conditions and the reagents that you need, okay? You need to use a concentrated nitric acid as your reagent. A catalyst is concentrated sulfuric acid. Conditions, you need to heat it under reflux at 55 degrees Celsius. So these are some of the things that you need to memorize, okay? So what happens is you will attach the nitro group onto the benzene and your other product would be H2O. Okay? When you have an NO2 onto a benzene, we call it a nitrobenzene. The mechanism, because it is still arene or benzene, therefore the mechanism is still electrophilic substitution. Okay? Moving on, just like the mechanism of halogenation of benzene, there is the first step where you need to produce the electrophiles, okay? So the first step is, again, not much, but mostly just memorizing. Your reagent, concentrated nitric acid, will react with your concentrated sulfuric acid to form your electrophile, nitronium ion or nitryl cation. So that NO2 plus is your electrophile, okay? And then you form HSO4 minus and hydroxonium ion H3O minus. So these two are not so important because they're just the side products of the formation of your electrophile, okay? NO2 plus is the one that will proceed further. Okay, moving on. This is where we are going to draw the mechanism. Again, nothing new. You all know this already. Please read the description. I will just draw the mechanism for you and describe and explain briefly. But again, there's nothing new. What color do I want? Purple, maybe. Okay. So the NO2 plus, the electrophile that you produce from the first step, will be attacked by the benzene ring. Okay, so a pair of electrons from the delocalized system, a pair means two electrons. Okay, so a pair of electron attacks the electrophile like that. Okay, and then you form an intermediate. Okay, the electrophile NO2 nitronium ion sits on that carbon because I like that carbon. Now it becomes carbon number 2. Okay, so NO2 initially has a positive charge, but once it's attached to the benzene ring, the positive charge is being spread over between carbon 1 and carbon 2 and carbon 6. So if I start numbering this will become carbon 1, 2, 3, 4, 5, 6. Okay, so in this unstable intermediate, there are only 4 electrons inside the ring. Okay, this is what I did not mention to you last time. Don't forget, on carbon number 1, there is a hydrogen that sits there originally. That carbon-hydrogen bond breaks, a pair of electrons is being donated to the positively charged broken delocalized system. The hydrogen is being released as H+. Okay, the delocalized system is restored, and then there's your NO2. So that's your nitrobenzene. Okay, this is your electrophile. Please read the description as you go along, yeah? Why can't I write? What is wrong with my stylus? Oh no. NO2. Okay, you get it. You get it. Okay. So this is your product. I just want to write, actually, that's why. Nitrobenzene. That purple is your electrophile. Why is it not so smooth? Electrophile. Okay. Okay, that's done. Okay, any questions? No, so we can move on. Right. So your nitrobenzene can be substituted further. Okay. But nitrobenzene as a side chain, it has the opposite effect to methylbenzene. Okay, just now I said methylbenzene is methyl group as a side chain is an electron donating group. So it donates electron density into the ring. That means the ring of a methylbenzene is more electron rich than the ring of a normal benzene. Okay. For nitro group, it's the opposite. It is electron withdrawing. That means it takes some of the density from the ring of benzene. So that means the ring or the delocalized system of a nitrobenzene has a lower electron density than benzene alone. Is that okay for you? Okay. Well, I'm asking and I'm answering as well. The thing about the nitro group is it also has the opposite effect on the activation of the position of carbon. Okay, methyl group would activate the 2,4,6 position. Nitro group will activate the 3,5 position. Okay, which is this and this. So that means, what does it mean by activating these positions? Any incoming electrophiles, whether it's NO2 plus or Cl plus or Br plus, these are the electrophiles that we've met so far. So any incoming electrophiles will choose to sit on the 3rd position or the 5th position or both. Okay, so it depends on the reaction. If you use excess reagents, then you probably will have di substitution, otherwise mono substitution. For this reaction, we will show you both the mono substitution and the di substitution. Okay, so I will draw the original molecule as blue. So that's my original molecule. Okay, I'll draw the product after this. Nitro group, I will make it orange. Okay, so you have a nitrobenzene. Now, if you have a benzene and you want to attach a nitro group, it doesn't matter where it sits. Okay, it can sit on the top carbon, bottom carbon, left top, right top, bottom left, bottom right, it doesn't matter. But once you already have this nitro group, and the fact that it activates the 3rd and the 5th position, so your incoming electrophile, which is also a nitro group, and oh my God, what is wrong? The NO2 plus will either sit on the 3rd carbon or the 5th carbon here that you cannot see. Okay, so when you draw the mechanism, you make sure you cut through that 2 bonds. I think I need to wipe my stylus. Okay, so the possible products, NO2. Make sure that the carbon of your benzene is attached to the nitrogen of your NO2. The other product is di substitution. Okay. Notice how I have drawn that the carbon is attached to the nitrogen of the NO2. These are the only 2 possible products. Okay. This is called 1,3-dinitrobenzene. The other one is called the 1,3,5-trinitrobenzene, which is already written in your notes. Okay. What did I want to mention just now? I forgot. Oh, 5 position. 5 position is actually the same as the 3 position. This, if I draw another product here, I hope you can see. 5 position is this position. Basically, these two molecules are the same. Can you see that? Miss, I don't see any drawing. Oh my God, that's right. What's happening? Maybe my internet connection. Let me stop sharing and then share again, and I hope it works this time. Can you see now? Yeah, okay. Basically, I was just talking. When did you not see? Was it the whole time that you didn't see the drawing? Stop blaming Ang, Eric. Okay, so what I was trying to say is this molecule is in the 3 position. Now you may think the bottom drawing is in the 5 position. Actually, that 5 position is also 3 position if you start counting anti-clockwise. Okay, so this 2 molecule is the same. That's why I do not draw them. I just have to draw one of them. Okay. Naming is already given in your notes. 1,3-dinitro and 1,3,5-trinitro. When you draw the mechanism here, please make sure, draw the arrow, cut the bond where you want, cut through the bond where you want to put your nitro group. Okay, so that's why you can draw the arrow here or the arrow here. Okay, don't draw it like this. Don't use there and then suddenly you put the NO2 at the bottom. Okay, my cursor is not responsive. Okay, any questions so far? No. Okay. Next, apply knowledge relating to position of substitution in the electrophilic substitution of arene. So, oh, next slide. Oops. Here. So this time I want to talk about the electron donating and electron withdrawing group. Okay. As you know, the example that we looked at before this was methyl. When you have a methyl side chain, it is electron donating group and it activates the 2,4,6. Okay, so generally, when you have an electron donating group, they activate the 2,4,6 positions. When you have electron withdrawing group, they activate the 3 and 5 positions. Now, fortunately, you don't have to memorize this because the table is given to you on your data booklet. It says page 9. I don't know, you'll have to check, okay? So these are all the group. Column on the left is showing you all the groups that are electron donating and they activate 2,4,6. Now, please do not be misled by this chlorine. Chlorine is actually an electron withdrawing side chain or side group, but it activates 2,4,6. Why it activates 2,4,6? Well, there is an explanation that you don't need to know for your syllabus, okay? But one thing you need to know is Cl is the only electron withdrawing group that activates the 2,4,6 positions. Okay, so if we go through this, NH2, NHR, these are your amine, primary, secondary, tertiary amine. OH is your alcohol, your hydroxy group. They would activate the 2,4,6 position. NHCOR is your amide. CH2 or any other alkyl group ethyl, methyl, propyl, butyl, they all activate your 2,4,6 positions. Cl is not electron donating, but it activates 2,4,6. Okay, so Cl is the only exception where it is not an electron donating group. Moving on to the electron withdrawing group. I will erase this. NO2 is your nitro group. Nitro is electron donating, it activates 3,5. NH3 plus, that's your quaternary amine. CN is cyanide. CHO-COR is your ketone aldehyde. This side chain or side group activates the 3,5 positions. COOH and COOR is your carboxylic acid and your esters. Okay, so how do we apply this information? So for example, I have, let's see, I have a structure like this. Say, let's choose NH2. Okay, this is my NH2. This is my phenylamine, which we will look at in the next few topics. And then I have an electrophile, incoming, E+. Okay, so if you look at the table, NH2 is under the electron donating group and it activates 2,4,6 position. Automatically, the carbon where your NH2 is sitting is carbon number 1. So the electrophile will sit either on the 2 position, 4 or 6. Okay, easy. Now, what if I now have the opposite group from the other group, which is CN, cyanide. Okay, my incoming electrophile, I have to erase this. My incoming electrophile will have an option to sit on the 3 or 5 position. Is that clear? One good question from the other block just now. What if you have 2 groups that have the opposite effect? One NO2 and the other one is NH2. NO2 activates 3 and 5, NH2 activates 2, 4, 6. So your electrophile, where does it sit? Any remaining slots. Okay? So when you have 2 groups combined, your incoming electrophile can sit anywhere. So in a way, the rule is broken. Okay, there's no specific rule that says, oh, the electrophile will sit on the 2nd, 3rd, 4th, or 5th carbon. Okay, right. That is all for today. Do you want to continue? Because I stopped with the other block here. The next one is, oh no, we can continue. Never mind. I take back my question. I take back my offer to end the lesson early. The next learning objective is to interpret the difference in reactivity between benzene and chlorobenzene. Okay, so the chlorine, when it is attached to the benzene ring, it acts as a deactivating group. Okay, the deactivating group, now we know that chlorine as well as fluorine, hello, oh my god, where is it? Okay. We know that fluorine has a high electronegativity. A high electronegativity means that the atom tends to pull the electrons to itself. Okay, so that's why I said just now, chlorine is electron withdrawing. Chlorine takes some of the electron density from the benzene ring. Okay, now, so chlorobenzene has now a lower electron density. than benzene. Okay, how do you see that? Benzene, we can say that this is rich, electron rich. Now, in the moment you add chlorine to the as a side chain, the chlorine will take away some of this electron rich region. So relatively, the electron density in your chlorobenzene will now be less negative. Okay, I know there is no negative charge on it, but we say that it is less negative. Now, because for the reaction of chlorobenzene or with any other benzene or arene, they depend on the attraction between the ring and electrophile, which is a positive charge. So if your ring is less negative, the attraction with the electrophile is also less. Okay, if your ring is more negative or higher in electron density, the attraction to the electrophile is more. Okay, so that makes the electron density around the ring rather less in chlorobenzene. It is, that makes the electron density around the ring, that's not right. It should say benzene, not chlorobenzene. Okay, chlorine makes the electron density around the ring less than benzene. It is less attractive for electrophiles, and so the reaction is slower. So this explains why chlorobenzene is less reactive than benzene. Okay, so please take note of that typo, which I should also take note on my notes for my future students. The chlorine is more electronegative and so draw electrons from the ring towards itself. This makes the electron less than chlorobenzene. Okay. It should say less than benzene. Okay, so that is all that I want to cover. No, let me check first, double check. Yes, that is all that I want to cover in this lesson. The next lesson, we will do Friedel-Crafts alkylation and acylation. We have 8 minutes left. Do you have any questions? Do you want me to go back to any of the slides? So I want to re-emphasize again, benzene is more electron rich than chlorobenzene. Benzene attracts the electrophile more than chlorobenzene. Okay? Okay. Questions? Hello, everyone. Don't you want to say something or anything to me? No? Okay. Right. If that's the case, then I will dismiss you now. Stop